Black holes represent one of the most extraordinary frontiers in modern astrophysics, regions where the known laws of physics seem to collapse entirely. First predicted by Albert Einstein in 1916 as a consequence of his general theory of relativity, black holes remained a theoretical concept for decades. It wasn't until the mid-20th century that significant technological advances allowed astronomers to collect indirect evidence of their existence. One pivotal moment came in the 1960s when scientists studying the Cygnus star cluster stumbled upon an unusual celestial object. This object, a brilliantly glowing blue star emitting intense X-ray radiation, seemed to orbit an invisible companion. Traditional explanations failed to make sense of this phenomenon, and it was eventually confirmed that the star was gravitationally bound to a massive, invisible entity, what would later be named Cygnus X1, one of the first widely accepted black hole candidates. Cygnus X1 lies about 6,000 light-years from Earth and possesses some of the most extreme characteristics in the universe. Despite its compact size, its gravitational field is so powerful that even light cannot escape its grip. This inability to emit or reflect light is what gave rise to the term black hole. Following the discovery of Cygnus X1, astronomers began identifying many similar candidates across the cosmos. Estimates now suggest that our Milky Way galaxy alone may contain over 100 million black holes. These range from stellar mass black holes, formed when massive stars collapse under their own weight, to supermassive black holes that sit at the centers of galaxies and influence the movement of stars and gas clouds over vast distances. The gravitational dominance of black holes affects not only their immediate surroundings but also plays a critical role in shaping entire galaxies. When objects venture too close to a black hole, they cross what is known as the event horizon, the invisible boundary beyond which nothing can return. As these objects approach the event horizon, they experience a dramatic stretching effect caused by the extreme difference in gravitational pull from one end of the object to the other. This process, known as spaghettification, pulls objects into long, thin strands, ultimately leading them toward the singularity at the black hole's core, a point where the laws of physics as we understand them cease to function. Despite the wealth of knowledge gathered over recent decades, black holes remain wrapped in mystery. They serve as natural laboratories for testing the limits of space-time and gravity, yet their true nature continues to elude complete understanding. In 2021, humanity reached another major milestone when the Event Horizon Telescope collaboration released the first direct image of a black hole. This image captured the supermassive black hole at the heart of the M87 galaxy, located over 50 million light-years away. The iconic photograph revealed more than just a blurry silhouette. It offered unprecedented insight into black hole structure and behavior. Detailed analysis of the image suggested that black holes consist of three distinct regions. The outermost layer is the event horizon, marking the boundary beyond which nothing escapes. Just beyond this is the photon sphere, where light itself becomes trapped in orbits around the black hole. At the very center lies the singularity, a point of infinite density where conventional physics breaks down entirely. These layers reveal that black holes are not simply voids in space but intricate and dynamic objects that challenge our deepest scientific assumptions. Each black hole exhibits its own unique traits despite sharing a general structure. These variations make it difficult to develop a one-size-fits-all theory, and many traditional scientific tools fall short when applied to such extreme environments. Since direct observation is impossible, no probe can survive the trip past the event horizon. Researchers rely on indirect evidence such as gravitational waves, X-ray emissions, and orbital movements of nearby stars to study them. Multiple hypotheses attempt to explain how black holes form and evolve. While most stem from the death of massive stars, others may result from complex interactions on a cosmic scale, including galaxy collisions or the merging of smaller black holes. NASA's investigations into the core of the M87 galaxy provided some of the most compelling evidence for the presence of supermassive black holes, reinforcing their role in orchestrating galactic evolution on an unimaginable scale. One of the most significant theoretical advancements came in 1963, when New Zealand physicist Roy Kerr introduced a groundbreaking model describing rotating black holes. Known as Kerr black holes, these differ from earlier models by including angular momentum. A key feature of the Kerr model is the ergosphere, a region just outside the event horizon where space-time itself is dragged around by the black hole's spin. Within the ergosphere, objects can still theoretically escape if they follow the right trajectory, unlike the event horizon, where escape becomes impossible. These developments continue to fuel curiosity and inspire further investigation. Black holes, once considered the stuff of science fiction, are now central to some of the most cutting-edge research in physics and cosmology. They push the boundaries of what we know about the universe, time, gravity, and even reality itself. Though we may never set foot near one, the study of black holes brings us closer to answering some of the biggest questions humanity has ever asked, about where we come from, what the universe is made of, and where, deep within the enigmatic heart of black holes lies a realm that defies the traditional rules of physics. This exotic region hints at deeper, hidden truths about the nature of the universe. One of the most intriguing concepts to emerge from theoretical physics is the Einstein-Rosen Bridge, or wormhole, a hypothetical tunnel through space and time that could link distant regions of the universe, or perhaps even different universes altogether. Rooted in Einstein's general theory of relativity, the idea suggests that spacetime is not a fixed stage, but a flexible, four-dimensional fabric distorted by mass and energy. A wormhole, in this view, is a kind of fold or tunnel in this fabric, offering a potential shortcut between far-flung cosmic locales. Despite its theoretical elegance, the idea of wormholes raises daunting questions about their physical reality. Theories suggest that intense gravitational forces and quantum instabilities within these structures might render them too unstable for use. Even if they could be stabilized, potentially through hypothetical exotic matter, Einstein's relativity still imposes limits on travel speed, likely preventing faster-than-light transit. While these obstacles cast doubt on the practical application of wormholes, the idea continues to fuel the scientific imagination, symbolizing the enduring human fascination with cosmic travel and hidden dimensions. This vision of cosmic tunnels and gateways is closely tied to the broader pursuit of a unified theory, a framework that would seamlessly reconcile general relativity, which governs gravity, with quantum mechanics, which explains the behavior of subatomic particles. Among the most ambitious candidates for such a theory is superstring theory. Promoted and advanced by visionary physicists, this theory departs from the notion of point-like particles and instead posits that everything in the universe is composed of tiny, vibrating strings. These one-dimensional filaments, like the strings of a musical instrument, vibrate at different frequencies to produce the variety of particles and forces we observe. In this view, the universe itself is akin to a grand cosmic symphony, with each particle corresponding to a unique note or resonance of these fundamental strings. Superstring theory has opened new avenues for understanding some of the most mysterious phenomena in the cosmos, black holes, wormholes, and gravitational singularities among them. As these strings travel through space-time, their interactions create distortions and structures that help explain phenomena previously thought to be beyond the reach of current physics. Yet, the beauty of superstring theory is balanced by its complexity. One of its more challenging implications is the existence of extra dimensions, beyond the familiar three of space and one of time. These additional dimensions are theorized to be compactified, curled up so tightly that they are imperceptible to the human senses and our current instruments. Metaphors like imagining a fish confined to a two-dimensional pond help us grasp how beings in lower dimensions might be unaware of higher ones. While we may not perceive these dimensions directly, their mathematical signatures could explain many of the universe's hidden properties and structures. These hidden dimensions offer more than theoretical elegance. They provide potential answers to long-standing questions about the behavior of gravity, the mass of particles, and even the birth of the universe itself. Superstring theory has also triggered a renaissance in mathematical physics, revealing deep connections between pure mathematics and real-world physical behavior. In this way, the pursuit of a unified theory has become an interdisciplinary journey, blending physics, mathematics, and philosophy into a single quest for ultimate truth. Despite its compelling framework, superstring theory remains unproven by direct experiment. Its predictions are difficult to test, largely because the extra dimensions it proposes exist at scales far smaller than current technology can probe. As a result, much of its exploration remains within the realm of theory. Nevertheless, the ideas it proposes continue to inspire a generation of physicists, pushing the boundaries of what we believe is possible. Recent developments have reignited hope in this long-standing quest. The study of quantum black holes, objects that bridge the gap between relativity and quantum mechanics, has made notable strides. Edward Witten, one of the most influential physicists in the field, once described superstring theory as 21st-century physics that fell into the 20th century, highlighting both its advanced ideas and the challenge of proving them. Now, new breakthroughs suggest that string theory may indeed help explain the quantum nature of black holes, particularly in simplified two-dimensional models. While this progress is promising, translating these findings to a complete, 10-dimensional theory remains a monumental challenge. The continuing quest for a theory of everything leads scientists into the deepest layers of reality, where abstract concepts and tangible phenomena converge. The stakes are high, as solving this puzzle could unlock the most fundamental truths about the cosmos. Understanding black holes is not only a matter of decoding their internal mechanics but also of redefining our comprehension of space, time, and the universe itself. Their interactions with other celestial bodies, such as neutron stars and gamma-ray bursts, unveil the dynamic and often violent interplay of forces that shape the cosmos. As humanity advances toward greater understanding, black holes serve as cosmic reminders of how much remains unknown. They challenge our assumptions, defy conventional logic, and beckon us toward an era of deeper discovery. Whether through superstring theory, quantum gravity, or a yet undiscovered framework, the drive to uncover the universe's ultimate design remains as strong as ever. In this pursuit, we are not merely studying distant objects. We are, in a sense, exploring ourselves and our place in the vast, mysterious expanse of existence.